Shiroman Prakash will give a tutorial on an elementary overview of string theory. Mr. Shiroman Prakash is a research scholar at the Department of Theoretical Physics, Tata Institute of Fundamental Research in Bombay. He obtained his bachelor's degree in physics from Johns Hopkins University in 2005 and received the Outstanding Minor in Computer Science award from Computer Science Department. He represented Johns Hopkins in the World Finals of Association for Computing Machinery.
Thank you for the introduction. All right, so the title of the talk is an elementary overview of string theory. So an outline of the talk is quantum mechanics and quantum field theory via path integrals, an overview of how we formulate string theory, and a list of some of its interesting features. Okay, so some comments. There will be no attempt made to create any explicit connections to nanotechnology, quantum computing, or quantum information theory. So what's the motivation of the talk? Perhaps only to gain a qualitative appreciation of quantum physics. Okay, it's also not yet known whether string theory describes the real world, but it's nevertheless an interesting theory to study. So, leaving aside string theory for the moment, quantum field theory is the best way we have of describing the elementary particles of nature. So the next few slides I'll try and give you an easy introduction to the subject. And just for a roadmap, as you can see, quantum field theory has two limiting cases. Classical field theory on one side, and the quantum mechanics of particles on the other side. And from quantum mechanics of particles, we go to classical mechanics. So there's two classical limits. It's a simplified diagram. And as you can see, quantum theories are green and slightly blurry. That's because quantum theories are slightly different from classical theories. Okay, so let's get a qualitative introduction to quantum mechanics and quantum field theory. And I'll not be able to discuss subtle features of quantum mechanics like entanglement, but I hope those of you who don't know quantum mechanics may get an idea. So say you arrived in Delhi from Mumbai. Someone asks you, how did you reach Delhi? You may say, okay, well, I took the shortest route, a straight line, as you pictured. And that's fine, but say you are an electron and Delhi and Mumbai were separated by some microscopic distance, then the answer would not be so simple. So the quote, when you come to a fork in the road, take it. That's R. Shankar used Yogi Berra's famous quote to explain quantum mechanics to humanities professors at Yale. So we can't say exactly what path the electron took. In fact, you may say the electron did not take any single path. It took a variety of different paths, and all possible paths connecting Delhi and Mumbai could have, in principle, been taken. So let's understand this better with a familiar example. You're all familiar with the two-slit experiment, so I'll not belabor the point. To find the probability that the electron starts out at A and reaches at B, you have to sum over the two paths connecting A and B. These paths may interfere constructively or destructively. If they interfere constructively, it's more likely to be at B. If they interfere destructively, it's less likely. So simple generalization. Now we have two slits, two screens. One of the screens has three slits. So instead of summing over two paths, you sum over 6 paths to get the probability distribution, as is obvious. So the obvious generalization from here is you add an infinite number of screens with an infinite number of slits. That's like there are no screens there at all. So that means there's an infinite number of paths the electron can take, and you have to sum over all those paths to get the probability amplitude. So what we do is sum over all possible paths which the electron could have taken. With each path, we associate a phase. The phase happens to be e to the I s of x of t. S is the classical action, for those of you who know classical mechanics. And these phases add and interfere to give the probability amplitude for the electron to go from A to B. So that's path integrals, Feynman path integrals. So now we want to sum over paths with more than one particle. So say an electron and positron start out with some velocities. What's the probability of them at some later time having, say, some different velocities or being at some different position? So we proceed as before. We have to do a sum over paths. So say there's no interactions. Then we just sum over paths which look like this. Treat the electron separately, sum over all the paths. Treat the positron separately, sum over all the paths you can take. And this sum over paths is not hard, actually. It just corresponds to a Gaussian integral. So I'm just representing all the paths by a straight line. Now say we add interactions. So how do we add interactions? We add interactions by adding an interaction vertex, which allows an electron to absorb a photon. Okay, then in this picture, we think of antiparticles, which the positron is an antiparticle of the electron. We think of these as electrons traveling backwards in time. So now you draw all possible paths, including the possibility of an interaction vertex. As you can see, there's now many possible types of paths, an infinite number of possible paths, which we have to sum over. And summing over all these paths is equivalent to doing quantum field theory, though I can't tell you exactly how. So that's quantum mechanics of particles and the quantum mechanics of field theory in a nutshell. We sum over all possible paths. And the paths could involve electrons turning into photons and vice versa. So what is quantum field theory? So ask Polyakov. He says elementary particles represent quantum excitations of some unknown medium, and we have an effective description of that medium's low energy excitations. So more familiar examples of quantum field theories would be excitations of a crystal lattice interpreted as phonons, or you may have some spins on lattice, take the continuum limit. So those are familiar quantum field theories. In the case of elementary particles, we don't know what the medium is, but we have an effective description of the medium's low energy excitations, which are quantum excitations of some unknown medium. Now it's not possible to do justice to the complexity of nature in our attempts to describe it using such a simple diagram. But anyway, here's a simple diagram we can consider. So most of the phenomena of physics that we study come under this side, originating in quantum field theory, which has classical field theory and classical mechanics as limiting cases. So electricity, light, radio waves. Then you come to quantum electromagnetism with photons. Similarly, if you want to describe billiard balls, you use classical mechanics. Atoms, molecules, you have to use quantum mechanics. Superconductors, really, the understanding is in terms of quantum field theory, but effective quantum field theory describing many electrons. Quarks, antimatter, that's the domain of quantum field theory. But there's more to physics than just these phenomena, namely gravity. So gravity is a classical field theory, but we can't make a quantum field theory out of gravity. So just a reminder of what are the phenomena that gravity includes. There's galaxy formation, black holes, expanding universe. These are the areas of general relativity. And in an appropriate limit, general relativity reduces to Newtonian gravity. Planetary motion and falling apples can be part of the game. So what's general relativity? General relativity is the classical theory of gravity. Space-time is a dynamical object whose curvature evolves in response to the energy it contains. The universe is expanding and appears to have originated in a singularity called the Big Bang. The universe may contain black holes, which are singularities surrounded by event horizons, which I'll describe later. So to understand these singularities, we can't use a classical theory of gravity. We need a quantum theory, but unfortunately, directly quantizing the gravitational field leads to infinite answers to reasonable questions. So we are in a fix. So the question is, why consider string theory? So the main reason is it's a quantum theory of gravity. So it may answer previously unanswerable questions about the quantum mechanics of black holes and the Big Bang. Second reason, maybe a unified quantum mechanical description of the fundamental forces of nature. And a third reason, it may just provide us a better understanding of quantum field theories. And quantum field theories are very important, as you saw from the last few slides. So here's another oversimplified picture saying where would string theory be. So in an appropriate limit, you may get general relativity out of string theory, and you may have a quantum field theory describing the effective low energy physics of string interactions. And to understand the Big Bang, really, we need some quantum theory of gravity like string theory. Same goes for black holes. String theory adds new features to quantum field theory that we consider, like extra dimensions and supersymmetry. And there's more to string theory than just strings, which is D-branes. So what is string theory exactly? String theory starts with the hypothesis that we replace point particles with tiny vibrating strings. And these vibrating strings are quantum mechanical relativistic strings. So how do we describe them? So here's a picture telling you the classical mechanics of a string. A particle traces out a one-dimensional world line in space-time, as you can see here. So if we draw the graph of the particle in time, you get a one-dimensional object. For a string, which at a given instant in time is a one-dimensional object, if we trace out its trajectory, we get a two-dimensional surface in space-time called the world sheet, which is pictured here. So what's the quantum mechanics of a string? We describe the quantum string by a quantum field theory living on the two-dimensional world sheet. So here's a blurry string. So for a simple string, there would be d quantum living in d space-time dimensions, say 4 for the real world. You would have 4 quantum fields living on the two-dimensional world sheet. So each direction x, y, z, and t, these correspond to quantum fields living on this world sheet. Okay. And what we do, like previously we were summing over all the trajectories, all the possible trajectories considering 2 points. Here we have to sum over all possible world sheets that we can draw. I won't go into the technical details of the sum, but anyway. Now we want the strings to interact. So how do we introduce interactions? Previously we had vertices connecting the world lines of the particles. Here we allow 2 strings to merge. When we're doing the sum over world sheets, we allow that possibility. So here we see 2 strings connecting, merging, and then separating again. Here we have 2 strings, they merge briefly, but then they immediately separate, merge again, and then separate again. And we have to sum over all such Riemann surfaces that you can draw. So these may be orientable Riemann surfaces, unorientable Riemann surfaces, and the study of such surfaces relies heavily on complex numbers. So, Witten said that the generalization from point particles to strings is as natural as the generalization from real numbers to complex numbers. So which is a very natural generalization. So now in string theory, the free theory uniquely determines the interacting theory, which must include gravity. So in particle physics, we could choose what interactions to add. You add any vertex you want, any factor you want. But if you tried to add gravity, you'd get infinite answers. In string theory, the situation is different, because everywhere it looks just like a single string. So there's really only one set of consistent interactions you can include once you describe a free string theory. And that set of consistent interactions necessarily includes gravity and doesn't give you infinite answers. So instead, we're just quantizing strings, and we see we have to get a quantum theory of gravity, which is the initial surprise of strings. There's another way of looking at strings. We can see how the strings correspond to particles. So the quantum relativistic string has discrete allowed energy levels. Is due to quantum mechanics, which causes atoms to have discrete spectra, and the classical mechanics, which causes the classical violence string to have certain allowed vibrational modes. So immediately you can see that the mass, so energy is mass in special relativity. So the states with energy 0, with massless states, include photons for open strings, which are strings with endpoints. For loops, massless states include gravitons. We can just see that by quantizing the string. So if you know special relativity, you may ask the question, okay, if energy is mass, then shouldn't any vibrating string have positive mass? And the answer is yes, classically, but quantum effects, conspire with special relativity to exactly cancel out that positive energy, so that one level of vibration is canceled out by the quantum Casimir energy of the string, thereby allowing massless string states. Now, it turns out that quantum string theory does not make sense in 4 space-time dimensions. I can't tell you why in this talk. But quantum mechanical consistency fixes the total number of space-time dimensions to 26 for a simplest string you can think of, or 10 dimensions for the more realistic string theories, super string theories. So we don't add the extra dimensions by hand. Quantum mechanics tells us that our theory doesn't make sense unless you have 10 dimensions. So we only see 4 dimensions if string theory is right. What happened to the other 6? Compactified is one answer. So that means they're really small and like circles. Exactly how they're compactified affects the particles and interactions we see in the remaining 4 dimensions. Physical arguments suggest beautiful geometric constraints on the allowed shapes of the compactified extra dimensions. So I mentioned superstrings earlier. I don't have time to go into the technical details of supersymmetry, but supersymmetry is a symmetry that mixes bosons and fermions. What are fermions? Fermions are particles, or you can think of them as quantum excitations of fields, which obey the Pauli exclusion principle. So 2 fermions can't be in the same quantum state. Bosons don't obey the Pauli exclusion principle, so you can have any number of bosons in the same quantum state. Bosons are like photons, fermions are electrons, quarks, etc. So the fact that you can even construct a symmetry that mixes bosons and fermions may be surprising to you, because they're really different, very different things. And bosons are, okay. So superstring theory means we have a supersymmetric field, quantum field theory living on the string, which has fermionic degrees of freedom as well. So the degrees of freedom corresponding to normal dimensions are bosonic. Now we added fermionic fields to the worldsheet of the string, so we can interpret this, if we want to, as strange fermionic directions in space. But that's just an interpretation, it's not necessary. And you have particle spectrums in string theory which are very realistic. Maybe realistic in certain situations. Now, how many supersymmetric string theories can you write down once you say that the string is not just, once you have the freedom to define any quantum field theory you want to living on the string, doesn't that say you have many theories? And the answer is there's only 5 theories with supersymmetry. And these symmetries are connected by dualities. And these string theories, it turns out, are connected by various surprising dualities. I'll not talk about T-duality, but what is a duality? A duality is when two apparently different theories turn out to have identical physical content. So the example is a theory with a very large extra dimension, maybe equivalent to a different theory with a very small extra dimension, which is surprising. Okay. Well, these 5 string theories are connected to each other via dualities, plus there's a field theory also connected in this game. And that leads people to suspect that the 5 10-dimensional string theories are all different limits of an unknown 11-dimensional theory called M theory. What does M stand for? We've not decided, but probably membrane, magic, or mystery. Or murky, is some critics of the theory say. So it may be intrinsically quantum mechanical with different string theories as different classical limits. So we don't really know how to describe it, but perhaps we need quantum mechanics if we want to describe it, if we want to understand it properly. That's enough about M theory. Let's go on quickly to the applications. So black holes. Here's a picture of Sagittarius A star, which is a possible black hole at the center of our galaxy. So what are black holes? Classical solutions of general relativity containing a singularity surrounded by an event horizon. So an event horizon is like a one-way surface. So it absorbs but does not emit. So you can enter an event horizon, you can't come out classically. And classically, you describe a black hole only by very few parameters. The total mass of the black hole, its charge, its angular momentum. But semi-classically, when you try and include quantum effects, black holes emit some radiation. They also have a non-zero temperature and a non-zero entropy. And the entropy is huge, much more than the entropy of a star. But the temperature is actually very small. So I won't tell you how we understand thermodynamics, but since string theory is a quantum theory of gravity, it turns out we can begin to understand the thermodynamics of black holes. And I'm saying understanding the thermodynamics of black holes is one of the successes of string theory, though there's much work to be done. And really, what is it? String theory allows us to look at black holes as condensed matter systems. So we're turning gravity into condensed matter physics. That's what string theory is doing. That's one way of looking at string theory. So now black holes are part of condensed matter physics. How do we understand black holes? Requires us to talk about these objects called d-branes. So we count the entropy of black holes considering stacks of d-branes. What are d-branes? They are these extended objects in string theory which you can visualize as sort of like walls which the open strings can end on. I won't discuss d-branes much, but quantum field theories have non-perturbative features, effects you can't see using a finite number of Feynman diagrams. So d-branes are one such effect in string theory. And endpoints of open strings are attached to d-branes. D-branes introduce a strange new form of non-commutativity in physics. N-branes in 3 dimensions are described by 3 n by n matrices. So if you can simultaneously diagonalize all 3, then you have normal coordinates. But if you can't simultaneously diagonalize them, then that's strange, and you can't know the x-coordinate and the y-coordinate simultaneously. And we make many scenarios for model building, trying to get realistic models which may look like the standard model, considering intersecting d-branes and the like. So the last topic of the talk is the ADS-CFT duality. So never mind the words ADS and CFT. What is this duality? Well, it was discovered by Maldacena in 1998, and it may have surprising calculational power. So what's the theory? Okay, so it relates boundary theories to bulk theories. So you may have some theory described in a space, like Minkowski space or whatever, with gravity. So that theory is dual to another theory, a quantum field theory, living on the boundary of the space, which does not have gravity. So as you think of a sphere, so inside the sphere you have a theory with gravity that's defined there. On the surface of the sphere you have a theory without gravity, and those two theories contain the same physics, is what the conjecture is. So gravity itself, theories with gravity are dual to theories without gravity in lower dimensions, which is a surprising conjecture, and it's still a conjecture, although examples have been checked. We don't understand the duality fully, but we're interested in it because difficult problems in one theory may be mapped to easy problems in another theory. So this leads to some people to think of string theory not as a theory of everything, but as a calculational framework which allows us to solve many problems in quantum field theory or quantum gravity. So using ASCFT, people want us to understand quark confinement. People are publishing papers recently looking for applications to condensed matter systems of thin films or who knows, high temperature superconductors. And it's a major focus of current research. We will see what fruits it yields, if any. So that's it. Concluding remarks. Considering the quantum mechanics of strings, we've stumbled upon something big. As a quantum theory of gravity, we can now understand black holes and other gravitational phenomena as the collective quantum behavior of vibrating strings, which is condensed matter physics, basically. All the string theories, the 5 string theories, are semi-classical limits of a single, unknown, intrinsically quantum mechanical theory. And lastly, there's a duality between string theories and quantum field theories. So when you're actually doing string theory, you may be just doing quantum field theory in disguise. So I hope this has given us a qualitative look at string theory, and understanding string theory will hopefully require a better understanding of quantum mechanics and the role quantum mechanics plays in describing our world. So that's the end of this talk. Thanks.
Thank you, Shiroman Prakash. We have a couple of minutes to take few questions. Yeah, sure.
Thank you for elegant talk. I appreciated it.
Okay.
I also appreciate how hard it is to do experiments in this field.
Yeah.
And I'm wondering, you mentioned that Hawking radiation exists,
Yeah.
but it hasn't been measured, has it?
It's too small to measure, so we can't measure it.
So should it be may exist, or is conjectured to exist?
Theoretically, it would exist. We've not confirmed that it exists by measuring it, but okay, of course, since it's too small to measure, there's no contradiction. But if you consider black holes, then quantum mechanically, then semi-classically, without using string theory, but just general principles of quantum mechanics, you expect Hawking radiation. That's all I'm saying.
So
Theoretically,
it should exist.
If it didn't exist, we'd be very surprised. Not from only string theory point of view, but just from then maybe quantum mechanics is wrong if it doesn't exist.
Thank you.
Planet?